Hello guys, this is prime concept. Now we want to analyze another concept which is electric dipole. We want to understand what an electric dipole is, right? Now di means two poles. So we're talking of two poles. Now what is an electric dipole? An electric dipole is a pair of point charges with equal magnitude, that is to say same size but opposite signs, right? That are separated by a distance, say d. What do I mean? If I have a positive charge and also I have a negative charge and their magnitudes are the same, say this is 2 microcoulomb and this one is minus 2 microcoulomb, same magnitude 2 and 2 but opposite signs. Why this is positive, this is negative. If I put these two together, this forms what we call an electric dipole. So an electric dipole is a pair of two charges with same size but opposite signs separated by a distance d. That is what forms an electric dipole. I believe this is clear and simple. Now, if we have two charges like I illustrated separated by a distance d, then how do we calculate electric dipole mathematically? Electric dipole mathematically is denoted by the symbol P. So, and dipole, electric dipole moment, is given by P equals Q, that is one of those charges, times the distance of separation d. So this is the formula for calculating electric dipole. It is given as P, electric dipole moment. P is equal to Q times d. Q is one of the charges and d is the distance that separates those two charges. Very simple. The next thing we want to consider here is torque, or the force and torque experienced by a dipole, by an electric dipole. Force and torque of an electric dipole. Now, if I have a dipole and I place a dipole in an electric field like this, so I have an electric field originating from this side. We have a charge, a positive charge around here, which creates a field like this. And I place a dipole within this electric field. Say I place one charge here, a positive charge here, and then say I place a negative charge somewhere around here. Now, what it means is that within this field, within this electric field, I have a dipole, right? And their distance of separation is this. So which I'm going to call d. So d is the distance separating both of them. So when you place a charge, remember from what we studied earlier, when you place a charge in an electric field, that charge will experience a force. Now say this is our source of electric field, which is assumed to be a positive charge around here. So it means with respect to this positive charge, there will be a repulsion. So this charge is going to have a force of repulsion pulling it away. So I'm going to call that force F, right? And we know that the force that this charge will experience with respect to our source charge is given by the relationship QE, right? Is going to be what? Positive. It's going to be moving away. Now, say we have this, you consider this with respect to your source here, it's going to experience a force of attraction to your source. It's going to be attracted. So that force is given by this, which is going to be what? Negative QE. Why is this going to be negative? Because it is pointing towards the negative direction. It is pointing towards the positive direction. Now, one of the things you would quickly see from this diagram or this illustration is that the net force experienced by this dipole, the net force experienced by a dipole, remember the two charges have equal size. While this one is pointing forward, this one is pointing backward. The net force is simply the sum of these two forces. So since they have equal magnitude, if you add them up, their net force is going to be what? 0. So this is one point you should understand. The net force of a dipole in an electric field is always going to give us what? 0, right? And the next thing we want to analyze is the torque that this would experience. If you watch this very closely, you would notice that because you have two forces, there's possibly going to be there can be a torque around it, because this would move, so it can experience a torque that can cause it to change direction or change position. Now, if I do this, if I try to get the perpendicular distance, because torque would always be with respect to a perpendicular distance. If I try to get this perpendicular distance, say this is inclined at an angle theta, I want to find this perpendicular distance. The perpendicular distance is going to be d sine theta. If you use your SOHCAHTOA, it's going to be d sine theta, this perpendicular distance, right? Now, let's take this to be our center, the center, or the midpoint between the two charges. These are midpoints. Now, I want to take the torque around the center. So what it means is that my torque, taking it, or my moment, anyone you want to call it, taking it around this center is going to be, remember, this whole distance is d sine theta. So if I'm considering just half of this distance, it's going to be half of this, right? So my torque is force. Torque is force times distance. Let's call it s. So it means that my torque here is going to be the force. Any force can go. So let's consider this. It's going to be the force QE times the distance. And what is the distance? It is half of this, right? So which is going to be d over 2 sine theta. So if I do this, I would have the torque, right? Now, if I want to now get the total torque, since I have this and I have this, the total torque here, my net or total torque, of course, your net force is 0, but your net torque is not 0 in this case because they don't have the same line of action. So your net torque is not going to be 0. So my total torque, let me just denote it as this. My total torque is just going to be 2 times of this value. And if you multiply this by 2, because you know that 2 will cancel this, so your total torque finally becomes QED sine theta. So this is going to be the formula for torque experienced by a dipole placed in an electric field, QED sine theta. Now, if you recall, I earlier told you that a dipole is denoted by the formula. A dipole is given by the relation P equals Q times D. This is the formula for a dipole. So what it means is that I can replace this QD in this formula with P. So if I do that, I would have my torque. My total torque is going to be what now? It's going to be PE sine theta. So this is going to be my total torque in that system. If you also recall from what we learned in mechanics under vectors, you would know that if you have the product of two magnitudes sine theta, this same thing as a vector product. So it simply means this can also, this is the formula, or this can also be written in vector form. It can be written as torque equals what now? P, this is vector form, cross E, vector form. So it's either we use this or we use this. So this is how we can find our torque experienced by a dipole in an electric field. So this is very important. Note, the first thing I gave you was P is QD. That is what an electric dipole is. The second thing I gave you was net force experienced by a dipole in an electric field is what? 0. Then the third thing I gave you is the formula for the torque experience, which is PE sine theta, or P cross what? E. Now the last thing I want to do, we want to get the formula for potential energy. And if this thing can be displaced through a distance, because if you leave this in this system, in this electric field, over time, this angle by which this, it will be, the angle will change, it would vary, because there's going to be a movement, right? Yes, the torque would cause it to move, thereby decreasing this angle theta. Now, if that is the case, it means we can find potential energy experienced by a dipole. So I'm going to rub this so I can have space. So potential energy, of course, I'm going to start from work done, right? Now, we know that since there can be a displacement, a change in that position theta, it means work can be done. Of course, then invariably potential energy can be observed there. So work done in an electric field by a torque is given by the integral of the torque times this, right? Let's say this is moving from theta 1 to theta 2. So if we have this is the formula for our work done. So what I'm going to do is I'm going to bring this torque, since I know the formula for torque, I'm going to bring it into this relation and try to integrate it to see what we can get. Now my work done is going to be integral from, if it is displacing from theta 1 to theta 2, right? I have PE sine theta, PE sine theta. Now, in order to oppose that negative sign, I'm going to take this as negative because I'm going to eventually get a negative sign there. So we have, of course, why I'm adding a negative sign is because of the integral, and then secondly, because the torque in this system, the torque acts in a way to oppose or to reduce the change in this displacement. So meaning that the torque should be opposite, right? So that's change in displacement. The torque acts such that this displacement would not be much, it will reduce. So that's why I'm introducing a negative sign here. Now, if I integrate this, I would have minus PE is a constant, so I'll bring it outside my integral. So I have PE outside, integral from theta 1 to theta 2 of sine theta d theta. So when you integrate sine, you should know from basic integral, when you integrate sine, it gives you negative cos. So I have my work as minus PE. So all I'll get when I integrate sine is negative cos theta, right? So I'm integrating from theta 1 to theta 2. Now notice that this minus can cancel this, it becomes positive. So this is another reason why I had to introduce it. Now, W is going to be what now? It's going to be PE. Since this would cancel this, now I want to evaluate. I would have cos theta 2 and boundary minus what now? Cos theta 1. So if you evaluate this, you have that your work done is going to be PE cos theta 1 minus what? PE cos this theta 2 minus cos theta 1. So this is what we have. This is our work done. Now, we can from here get our potential energy, right? So we're going to assume our potential energy to be the negative of our work done. So if that is the case, our potential energy, P, potential energy, or let's denote it with U, which is the standard symbol. Our potential energy, U, is going to be what? Now I'm going to take this minus PE cos, let's generalize, cos theta. So this is the formula for my potential energy, while this is the formula for my work done. Now, if you recall from vectors, you would notice that whenever you have PE, whenever you have two quantities multiplying and then you have cos, it simply means dot product, right? So I can simply write this in another form by saying that U is what now? Minus P, the vector form, dot what now? E. Sorry, dot E. So is either I use this or I use this, depending on what I am given. So my potential energy is minus PE cos theta or minus P dot E. I believe that this concept is very clear. So we have been able to derive about 3 or 4 formulas from this. We mentioned an electric dipole. We said an electric dipole is a pair of point charges with same or equal magnitude but opposite sign, separated by a distance d between them. We also established that the net force experienced by a dipole placed in an electric field is going to always give what? 0. We also established the formula for the total torque experienced by a dipole. Then we derived the formula for work done and then the formula for potential energy. So do well to note all these relationships. In my next video, I'll try to take examples under this. Thanks for watching. Do well to subscribe to my channel, like my videos, and share with your friends so that they can also benefit. Remember, this is Prime Concept. Thank you.